boom. I'll go full screen or whatever on, maybe not. There we go, that's what I want. So I decided to do extra stuff. There were like chapters that were skipped over in just in Moran's lectures, and I think, so we did, when I took this course, we did Cauchy sequences, and I was kind of surprised that he didn't. It's probably like a time thing.
He definitely did talk about it.
He did? Okay, good.
He did. I think it might have been brief, but...
Okay, then in that case, we will talk about it a little more. Yeah, a little bit. I don't know if you've done this proof or not, but if you haven't, then we'll do it. And if you have, then it'll be easy. I'm recording, right? Yes, okay. So yeah, a sequence is Cauchy. If it's kind of like, the definition is similar to convergence. The idea is that, like, how do you phrase it? Points get arbitrarily close to each other is kind of like the best way to summarize it in a word. Whereas convergence is like, points get arbitrarily close to something, right? So like if, usually when you're thinking of convergence, you're thinking like, it's getting close to some like L, right? Either way. Cauchy is like, the points are getting arbitrarily close to each other, which seems similar, and it is similar. But yeah, it is similar. There are unique cases where, how do I phrase this? Well, all convergent series are Cauchy, but not all Cauchy sequences, but not all Cauchy sequences converge. So that's kind of interesting. And then you look up on the board and you see the proof that says, you know, prove that the sequence is Cauchy if and only if it converges to some point. Well, the key here is that we're talking real sequences. If we were talking complex sequences, this would not be true. It would be one way. Convergent always implies Cauchy, but Cauchy does not always imply convergent. But we're in real analysis, so when we're restricted to reals, then yes, it is, they're equivalent. So that's the proof. Maybe I should write out the definition of Cauchy. So the definition of a Cauchy sequence is that for all epsilon, there exists an n, is this right? Yeah, n in n, such that for all n and m greater than or equal to n, x sub n minus x sub m is less than epsilon. So it's basically the same definition. This is for Cauchy, just with the x sub m's and x sub m's. For convergent, it was for all epsilon greater than 0, there exists an n natural number, such that for all n greater than or equal to n, absolute value of xn minus L is less than epsilon. So the difference is your xm versus L. Yeah, so that's it. See if you can prove it. I don't know if anyone's online. I don't think so. They're all busy with other midterms, I think.
I guess so.
There's a bunch of messages on the Discord channel, and apparently now they're not doing the quiz, so that's fine by me, I don't care, but it seems like those kinds of situations never end well.
No.
It's like you ask for it the next week, but then the next week is always going to be more terrible than the week it originally was, and yeah, never works out well, from my experience.
Also, you always end up with some people who the original date worked better for.
Yep.
Right?
Yep.
So that's me.
Yep,
That's me this time.
doesn't surprise me.
I got way more to do next week than I do this week.
Yep.
But
Yep, that happens.
we also, have the assignment for this class next week.
Yep, and the midterm's next week, isn't it?
Week after.
Oh, the week after, okay. Oh, that surprises me. I guess it makes sense, but yeah. And what's the midterm covering?
That is a very good question. I don't think I've looked at it.
Sure, neither have I, but I will for tomorrow. Now, I don't know what midterm Moran is using, but I assume it's different from the one that I took so many years ago, whatever it is, 3 years ago. But on the midterm that I wrote, there was a question on Cauchy, and every single person got it wrong because, and it was an easy one too, and it was worth like a lot of marks. It was like, write out the definition of Cauchy. It was like nobody wrote down the definition of Cauchy on their cheat sheet or whatever, and nobody remembered it, and it was like, it was like, I think it was like a 5-question midterm or something like that. I'm probably mistaken, but it was something along the lines of like a 5-question midterm, and each question was worth 20 marks, and that was one of the 20-mark questions, and it was like, ouch.
The less questions there are on a midterm, the worse it is.
Yeah, but that's not even a hard question. Like,
No, it's
write
not.
the definition.
Which makes it so much worse when you get it wrong.
When every person in the class gets it wrong. Yeah. So those little definitions are good to know. Or he's giving you a cheat sheet, right? Yeah, neither do I. But
He's given it to us for the quizzes.
oh, then probably.
I don't know if that will extend to the midterm.
Probably. I have a hunch he'll give you like a, I don't know, letter size sheet of paper or something. He usually does that.
Yeah, I think that's. Actually, I think the quizzes are just bringing like notes as long as they're handwritten.
Yeah,
I
no,
don't
that's
think that
not the
was-
case for the midterm.
But yeah.
Yeah, he wouldn't do that for the midterm.
Is there a typo in the definition there? Absolute value of x n minus absolute value x n minus epsilon?
It's supposed to be less than.
Less.
Yep. The keys aren't even close, so I can't make that. It's supposed to be less than.
Okay. That's what I thought it was.
Yeah.
I was like rereading it and rereading it. Like, that's not a statement.
Yeah, that's not a statement. Yeah, no, it's less than.
Okay.
Did you do this one with you guys?
I think maybe. I don't remember it if you did.
That's all good. That's all good. I'm glad that he did to some degree. I'm pretty sure he didn't do the other two that I'm going to cover, but just going to get out the good old textbook. Yeah, it's such a weird book. So I think that's a proof for convergence implies Cauchy. So just use it as a triangle.
No, it is a triangle inequality.
Yep.
I got approximately the line 1.
Great. That's fine.
I chose to like get the M.
Okay, yeah, that's fine.
I was trying to remember the triangle inequality.
It works for
I
M2,
decided to-
right? So
Yeah.
yeah,
Yeah. So it's,
just letters.
And then would it be easier to do it just directly or by counterpositive?
That's a good question. How would they do this?
Most of the time I have to do a bidirectional proof. I just do one directly and one by the contrapositive. But
I'm wondering, because the triangle inequality only works the one way, I'm wondering if that would mess it up. Let's see what they did in the textbook. They use Bolzano-Weierstrass. You guys have done that, I assume? Crap.
I could not tell you.
Okay, sure.
We might have.
Okay,
It was a while ago for a lecture.
it's good that you might have. Let's see if I can pull up the Bolzano-Weierstrass. So, let's see. We'll just follow through the textbook's proof because it's probably going to get a bit gross. It's one of the ones that are like printed in the textbook as opposed to like being an exercise. So, Bolzano-Weierstrass is every bounded subsequence. Oh, sorry. Every bounded sequence in R has a convergent subsequence.
Yes, we did talk about that.
Cool. Good. The proof is like 2 pages long, so I'm not proving that, but I'll prove this. So, it says, suppose that the sequence is Cauchy, sequence xn. It says, given epsilon equal 1, choose a natural number n such that x capital N minus xm is less than 1 for all m greater than or equal to n. So then by triangle inequality, it says, let's see, xm is less than 1 plus xn. So capital N there. Still for m greater than or equal to n. So therefore, it says, therefore xn, sequence xn is bounded by, so let's see, sequence xn is bounded by m. You're using a lot of m's and n's in this proof, which I don't really like, but that's okay. The max of x1 through xn minus 1 and then 1 plus xn. Now, why is that? That's weird. Do you see that?
Yeah.
Yeah.
It makes sense to me, right?
Yeah. Because it's Cauchy, and because it's Cauchy gives you all of these, right? And then this thing gives you the last thing. And then you can apply Bolzano-Weierstrass. So there's a convergent subsequence. So it says, let's just say x and k is a convergent subsequence. So we'll say x and k approaches a as k goes to infinity. So it says, since xn is Cauchy, so since xn is Cauchy, it says choose some capital N1. They really like using n's and m's, eh? N1 and n, such that k is greater than or equal to n2 implies x nk minus a is less than epsilon over 2. Is that right? I'm going to skip something here, because that would be literally it. X. So since we have Cauchy sequence, choose that N1 such that, that's where I jumped the gun. For m and n bigger than that n1, we have x m minus xn is less than epsilon over 2. But it says, since x and k goes to a, as k goes to infinity, just choose x, choose n2. Such that k greater than or equal to n2 implies that x and k minus a is less than epsilon over 2. then it says, this is an ugly proof, fix k greater than or equal to n2 such that nk is greater than or equal to n1. And then you get x n minus a is less than or equal to x n minus x n k plus x n k minus a, which is less than epsilon over 2 plus epsilon over 2, which is less than epsilon. That's triangle inequality. Does that make a margin of sense?
A little bit.
Good. That's all I expect. Because that's the same for me. This proof should make sense.
Yeah, that one makes perfect sense.
Yeah, this one should be like,
That one makes a lot of sense.
yeah, it's ugly. So what did we do? We started off supposing it's Cauchy, use the definition of Cauchy, use triangle inequality to like rearrange this. The triangle inequality had been rearranged. So then we've shown that it's bounded by this maximum. Xm is less than xn, or absolute values at least, by by this, and then it's less than this just because of the triangle inequality. And then from there we have a convergent subsequence. It doesn't really even matter what it's, like what these terms are, because they don't get used as long as you know that this term is always going to be less than those. So that means it's bounded, so you can use Bolzano-Weierstrass. And then you just do a bunch of playing around with numbers, with n1s and n2s, to, applying the Bolzano-Weierstrass here, sorry, not Bolzano, a definition of Cauchy here, definition of convergence here, and then just merge the two together, and you get that. It's ugly. All right, let's move on, and hope that the next one's not as ugly, although I feel it's going to be. Cluster points. So, what is a cluster point? This is one of the funky things in the textbook as well. So, it says let E be a subset of R. Then a point A in R is a cluster point. Of E. If, and I guess only if, E intersect with A minus R, A plus R, contains infinitely many points for every R greater than 0. Yeah, that's ugly. Let's see if Google has it. It might. Let's see. So a limit point, accumulation point, cluster point of a set S in a topological space X. So in this case, R is our topological space. Should zoom in a bit. Is a point X that can be approximated by points of S in the sense that every neighborhood of X contains a point of S other than X itself. A limit point of a set S does not have to be an element of S. There's a closely related concept for sequences, a cluster point or accumulation point of a sequence. That's what we're referring to. a sequence in a topological space X is a point X such that for every neighborhood V of X, there are infinitely many natural numbers n such that Xn is in V. That makes sense. So you have Xn, it's a sequence of real numbers in this case, we'll say. They don't specify that, but we can. Then we say that X in that sequence is that right? X in R, because X, A is in R here, so A is our accumulation point. Maybe I'll keep notation consistent. A is in R such that for every neighborhood, you know what a neighborhood is, yeah?
Like an interval.
Yeah, it's like a
Like an interval centered somewhere?
an interval that contains a certain point and some points around it, an open interval.
Okay.
So like, the idea is like the neighborhood is like some, you know, arbitrarily small area around, you know, some point. Yeah. So it says, such that for every neighborhood V of X, so the neighborhood is some subset of R that contains A in this case. There are infinitely many natural numbers n, such that X sub n is in V. So there's infinitely many natural numbers n such that Xn is in V. Yeah. Infinitely many things in that sequence that lie within that neighborhood. You call that a cluster point. So like, let's think of a cluster point. If you had like a graph that was like sine, I think every point, well, let's just say for sake of simplicity, that you have the sequence sine of pi, n pi over 2. So that should give you like 0, 1, 0, -1, 0, 1, 0, -1. So that would be like 0, 1, 0, -1. Like that. All of those are cluster points, right? Because there's infinitely many points that lie around. Does it count X, is my question. Infinitely many natural numbers n such that Xn is in V. Yep. So it, by this definition, it does count Xn itself. I wonder if our original definition does. Let E be a subset of R, a point is called a cluster point if that interval contains, so that interval is your neighborhood, right? So it's some arbitrarily small neighborhood around A minus R, A plus R, it's an open interval. Contains infinitely many points for every, no matter how small of an interval you choose, right? In this case, we can, right? Because if you picked an interval that was like, say, 0.1 around 0, so if A is 0 and R is 0.1, you're always going to have infinitely many points for this sequence that lies within that. right? And you could pick any small r because it's always going to work, right? I believe you could even do that for something like sine of n. I think every point in sine of n, or between 0 and 1, is going to be a, now that would be a harder proof to show, but, so let's see the questions here. So it says, prove that A is a cluster point of E, if and only if for each R, E intersected with that interval without the singleton A is non-empty. So they must not count A in this case. Any ideas?
Write down the definitions and
See what comes?
see what happens.
Yep, that's a good start. So if you want to show
I
that,
think showing that A is a cluster point means that like the first direction is seems fairly easy.
like we
Right?
assume.
If I assume that that contains infinitely many points, then if we remove one point, of course it still contains infinitely many.
Yep.
Right?
Yep, that seems trivial to me, yeah.
The harder one is backwards,
Yeah,
unless there's
I see what
a
you're
flaw
saying.
in like firsts.
assuming that A is not in E, right? I think that's kind of the tricky part. Doesn't really specify that, but it might imply that. Let's assume that it implies that there's, that there's infinitely many things, like the definition of a cluster point said there's infinitely many points that aren't A in that set, for every r greater than 0. So, yeah, you're right. If there's infinitely many points, you remove A, you still have infinitely many. And then the other direction, if it's non-empty, how do you show that there is infinitely many things there? It has to hold for every r greater than 0.
No, that doesn't really. Just doing the contrapositive doesn't really work, I don't think. At least not cleanly.
Assume that that thing is empty.
Or like assume A is not a cluster point of B, then we have to show that that is empty. I guess,
Assume A is
for
not a
some r
cluster
greater than
point.
0.
Show
Oh,
that it's
wait,
empty.
no. For some r greater than 0, take absolute value of A. And then, no, there might be negative 2A to 2A.
Well, what's the inverse of that statement, right? Go back to discrete, so it says, yeah, we have that problem, right? So it says for all r greater than 0, E, no, not, there exists, E intersect the interval drop A is non-empty. So the opposite of that is there exists an r greater than 0 such that E intersect A minus R, A plus R, drop A is equal to the empty set, right? You could add a, so you would get, there exists r greater than 0 such that e this is equal to the singleton a. I don't know if that's any easier. So can we, if we assume, if we suppose that A is not a cluster point, then that means that there exists an r greater than 0 such that E intersect A minus R, A plus R. That thing contains infinitely many points for every R. So in this case, there exists an R such that this is less than infinite. Cardinality, that's less than infinite. So if we have found such an R, is there a way for us to show that it's actually, it's less than infinite, it's actually just the singleton? What if we assume there's something else in that set? Does that give us an issue?
No, it has to be between a minus r and a plus r. So it has to be less than or equal to both.
Mm-hmm.
Then you add r on all sides, positive, so it doesn't do anything to the column. You get a is less than or equal to that number plus r is less than or equal to a. Does that work?
Sort of.
No.
Lost.
So if suppose for sake of contradiction,
Yep.
there is some number, whatever, y, k, in the intersection of e and the interval,
Sure.
then because it's the intersection
Yep.
of the interval and e, it has to be in the intersection, or it has to be in the interval.
Yep.
So because it's an open interval,
Yep.
then it has to be, like a minus r has to be less than because it's in the interval, that means a minus r is
Yeah.
less than yk. And I don't know why I said yk, it's not like a sequence or anything.
Just change it to y.
Is less than a plus r.
Yep. So we'll
And if you add r, then you I guess, no, pick y minus r. No, never mind. No, it breaks down. Because there's nothing to say that y minus r would have to be in the set, right?
Yeah.
You say that y minus r is greater than a and less than a.
Y
Is that
minus
in itself
R
a contradiction?
is greater than A and less than A.
Or I guess, hold on. No,
Yeah,
they're different signs. I don't know what I'm even talking about.
But you could get rid of your A, right?
Yeah.
I don't know if that helps at all,
So you get rid negative r is less than y.
which makes sense, that's sort of assumed, right?
Yeah.
Because in order for it to be in there, it's gotta be in between those two. So there's gotta be some, oh, and I guess this should be y plus a, right?
Yeah.
Or minus a, probably. So the absolute value of y minus a is less than r. Does that tell us anything? distance between y and a is smaller than r, which makes sense. I don't know.
It's not working out the way I thought it would.
No, because we're working on an existential, so it's not like we could say, well, this doesn't hold for every r,
Yeah.
right?
There's some R that needs to hold for.
Yeah. And that r could be like 1, in which case,
Yeah.
be perfectly fine. Maybe, but, yeah.
This is the wrong approach.
That's tricky. What about if we go back here? These are all fine. Suppose A is not a cluster 20. Then we found some R so that it's in that range. Oh, sorry, so that that set is less than infinite. So why don't we just give some notation? Let's just say that E intersect A minus R, A plus R, we're gonna define to be equal to like E1 through E n. So what we want to show here is that E1 equals E2 equals En equals A. They're all the same. What if we suppose that we have two things in the set? What if, suppose you have A and A bar in that set? Such that A is not A bar. Do we run into any problems? Or can we construct infinitely many things that are also in that set in some way? I don't know. How's our time? 3:15? Okay. I'm gonna think on that, and I'm gonna put up the next question, which is easier. I'm actually gonna Google on that because I'm lost enough to need to know the answer. Oh yeah, I should introduce what a limit infimum and limit supremum are. This is chapter 2.5 of the book. So it's pretty self-explanatory. The limit infimum is just the limit of the infima. And the limit supremum is just the limit of the suprema. So we define the lim sup of x, or as n goes to infinity, of xn to be equal to the limit as n goes to infinity of the supremum for k greater than or equal to n of xk. And the same for the infimum. The limit of the supreme, sorry, not the supremum, the infimum of xn as n goes to infinity is the limit as n goes to infinity of the infimum of k greater than or equal to n xk. Your job is to show the sort of negation properties of this. So negative limits supremum of xn is equal to the limit infimum of negative xn. And the opposite, that the limit infimum of xn negated is the limit infimum of, limit supremum of negative xn.
Is it fine to use the theorem from class where the infimum is?
Yep.
Yeah, okay.
Yep. But you still have to deal with the limit, right?
Yeah.
The negation of a limit is the limit of the negation, which have you proved that?
Not yet.
That's your proof then.
Definitely in calculus.
Oh, it's pretty obvious, but
Definitely in calculus, that you can take the k out of the limit,
you sure can.
and the negative one is like the k.
But why? That's why I did that.
Yeah, so I'm gonna do that with an epsilon delta.
Yep.
That's not fair, we haven't done that in class.
You haven't done epsilon delta in class?
No, I don't think so.
Okay.
Unless I was
then,
like staring at my phone instead of paying attention. But I think we talked about epsilon delta stuff yet.
probably not. Have you talked about the connection between limits and convergence?
I don't know if we've got the limits
At all?
at all.
Didn't you do squeeze theorem and shit?
We did. We definitely got the limits. You're
Yeah.
right. Maybe I just wasn't paying good enough attention.
Maybe. Well, it's the same as calculus.
Actually, I think I zoned out around the time of squeeze theorem.
Okay. So let's
So we
see.
probably did talk about the epsilon delta, I just don't remember it.
Okay.
Was it x minus a less than delta implies absolute value
F of x minus L.
is less than epsilon.
Yeah, so limit as x goes to
Oh, I want to show
And-
f of x.
I guess we could say limit as n goes to infinite of xn equals L is the same thing as limit. Well, this is the same thing as xn, the sequence xn approaches approaches L as n approaches infinite. Right? It's just convergence. Limits are different when you have like, say like x approaches a, that's a different thing, right? Where it's not infinite.
Yeah.
But we've been dealing with the infinite case, just under weird notation. So this is the same as this. And this is the same as for all epsilon greater than 0, there exists an n greater than or equal to, exists an n natural number such that for all n greater than or equal to n, absolute value of xn minus L is less than epsilon. So you'll have to prove the negation thing using that crap. or more specifically, you'll want to show that x, let's see, the negation of xn approaches the negation of L as n approaches infinite. That'd be your like lemma.
That's just a negative sign on the xn and on the L, which I
Yep.
factor out, and that's an absolute value.
You don't even have to factor it out, right?
No?
Or I guess, yeah, you can factor it out.
Factor out, and
Sure.
then the absolute value is multiplicative.
Yep.
So you just end up with the exact same thing.
Yep. You do.
And that's the proof? More
That's the proof
just with more notation, without.
with more notation. Yep. Let's see if Google can give me anything on the cluster points. Paste. Well, somebody's tried it. Yeah, so one direction needs proof for this guy. So they wrote, suppose A is not a cluster point, you have this. We were close. So that actually we'll do econometric. Yeah. This is kind of trivial.
What's the notation of the E?
Oh, ball, like a circle, or I guess you could say in this case, an interval.
Okay, yeah.
The interval, what was it, it's, x, what is it, centered at A. So I'll just leave it as, ball of d over 2 at A. All of d over 2 at A is gonna be, A minus d over 2, A plus d over 2. Yeah.
So we're thinking about shapes on
One dimension.
line.
Yeah.
Like, it makes sense. The mathematical definition of a ball is every point less than, some distance away from the center point. It's just, that's an interval.
Yep. Yep. That's That's the way we do it. Interval is a one-dimensional circle.
Intersection with. What is D?
So D is the minimum over all I. Maybe I should write this a little nicer. The minimum over all I less than n. So between 1 and n. So the minimum distance between, like, I'll verbalize this a bit better. So you have this set, right?
Yeah.
If we sort of just get rid of this piece because we ignore this,
Okay. No, I think I'm following.
assume that this is finite, then, well, assume that E intersects the ball at a radius r, which is this. The cardinality of that's less than infinite, then that means if you knock off A, it's still less than infinite, right? So your goal is to show then that this is the empty set for some r. So we're just picking, here we're just picking r equal to D, which is the minimum distance between any of those finite xi's and A.
And then take D over 2, obviously, even the closest isn't within that. Okay.
Yeah.
Like now.
Exactly. Yeah, and then that's it, right? Because nothing's gonna be in that set. So you've found such an R, so that it all sort of breaks down. Do a contraposition and a contradiction. It's ugly. That's it for time, probably? Yeah, pretty much. So we're doing midterm